Okay, so welcome back. This is part 6 in our series where we help you to understand this device, which is a switching ATX power supply used in desktop computers. Now, keep in mind that the major functions inside this power supply are used in many different locations. Your motherboard, GPUs, and other equipment uses similar concepts. So it's really important to understand the basics of how these work. In the previous videos, we looked at the input section where you take the electricity from your wall outlet, which comes from your power company. In the US, it's 120 volts RMS, 60 hertz. We talked about some of the things that the power company has on their side, so you better understand why you need some of these components here. And we have, for example, we've got some overvoltage protection in the form of an MOV, metal oxide varistor, which is very similar to what the power company has on their side. And we talked about that. We talked about some of the filtering, the full wave rectifier bridge. Basically, at this point, it comes into a DC, about 170 volts, with some ripple. And then in the previous video, we started to get into this section here, which is the buck converter, which converts that 170 volts down to the 12 volts and the 5 volts and the 3 volts that ultimately gets fed to your computer or whatever device. We also, in a previous set of videos talking about myths surrounding these computer ATX power supplies, we actually did some bench tests here to apply a short circuit to this power supply to verify that, in fact, contrary to what people like to believe, there is a device here, which is an integrated circuit, which in quality ATX power supplies, the specification requires that there is some protective circuitry in here to make sure that the output current going to your motherboard or whatever device doesn't exceed the rated value. If so, it will send a signal to the switching power supply to shut off and protect your device. So in this video, we're going to talk a little bit deeper about this buck converter, which brings the voltage down to 12, 5, or 3 volts. And in the previous video, we showed how the circuitry we had actually responds to applying a heavy load, but in the simple circuit we had before, it didn't recover fully. So what we're going to do in this video is we're going to look at some little tweaks we can use for this buck converter to make it recover to our 12 volts going to the motherboard. We're also in this video going to look at a very simplified version of this integrated circuit to show how we can, with some simple logic, generate a signal. If the current exceeds rated value, it will generate a signal and shut down this switching buck converter to make sure you don't damage the equipment. So I encourage you, if you like any of these videos, hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Now, one thing you want to look at before we get into this is notice these big inductors. All over this motherboard, we have lots of big inductors. And that implies that when we do our design for this buck converter and other circuitry, we're going to need some big inductance values, because what we're doing is we're switching with a high frequency, and we're going to want to filter that down to a very flat, low voltage. So we're going to need some big inductors. So when we start to get into this analysis, we're going to say, hey, we need to get some big inductors to make sure that we've put the voltage where we want, nice flat and filtered voltage. So now let's go into LTSpice, which we're going to use to simulate this as we have in the previous videos, and take a look at this buck converter and see if we can tweak it a little bit, and then start looking at these protective supervisor circuits. Okay, so here we are in LTSpice. Now, if you haven't used LTSpice before, I encourage you. It's a great way to learn electronics. And if you know electronics, if you have a circuit you've designed, you want to see if it's working the way you expected, it's a wonderful way to do it. It's a free piece of software. I've done a series for beginners on how to use LTSpice, and we've used it in many of my other videos. It's a really wonderful way to understand electronics and to verify your circuits you've designed. Now, this is a very simplified circuit for a switching power supply, but the concepts are there, and once you understand the basic concepts that we're going through, it'll be a lot easier to understand the details of a specific design. Now, in the previous videos, we talked about this left-hand side where we basically take our, here in the US, 120 volts RMS, 60 hertz from the wall outlet coming from the power company. And it's got some filtering and some overvoltage protection here. And we looked at even what's on the power company side, their overvoltage protection and their transformers and everything else. Coming out of that circuit from the previous videos, we've got our full wave rectifier and an RC filter. And what we're going to look at in this video is basically the right-hand side here after this V in. And in the previous video, we looked at the three main components of this circuit. Up here, you've got a buck converter, which takes our 160, 170 volts DC with some ripple and brings it down to about 12 volts. And we've got the switching MOSFET that operates this switching transformer for the buck converter. And then we've got this PWM controller that we talked about in the previous video. And this basically measures the output voltage through this feedback circuit. When it's at 12 volts, it doesn't do much, but when it's outside the range of 12 volts, it modifies the PWM circuit to give us, to return to 12 volts. And over here, we've got a switch that after about 10 milliseconds applies a heavy load to this so we can watch the transient response to make sure everything's working, and it applies a 72 watt load. So in the previous video, we looked into some details, and we found out that the circuit the way it is now works pretty well, but it doesn't quite meet our need for a 12 volt output after we switch this. So let's take a look at where we are, and in this video we're going to look into some of the details of this buck converter to see how we can get a little bit better performance. And I've also added another thing we can discuss in this video, which is the protective circuitry you generally will find in an ATX power supply. And one of the things we're going to model is the ability to monitor the output current coming out of your power supply into your computer or whatever, and sense if the current is getting over the rated current. And what it will do, I've added a little bit of circuitry here that will automatically shut down our PWM circuit, which shuts down this switching transformer and the MOSFET, and suddenly makes the output go to zero to protect your equipment. Now, we've also talked in previous videos about that functionality in a real ATX power supply, and we actually applied to an ATX power supply a short circuit and looked at it on the scope and saw that, yeah, in fact, this thing actually does work to shut off the power supply instantly as soon as you go above rated current. Contrary to what a lot of people like to believe, that, oh, if you get a short circuit on your computer motherboard, your computer's going to blow up because these power supplies don't do anything. Well, actually, the ATX specification says, no, that's not true. So we looked at that, and what we're going to do is we're going to put in a very simplified version of that to show the basic concept on how you can measure the output current and shut this down when it exceeds the value. So let's first look at, again, we're going to kind of ignore this left-hand part in this video, and we're going to start with this V in. So let's look at the V in that we're getting at this point right here. As we expect, it's about 160, 170 volts, almost DC, and you can see it gets a little bit of ripple. And as we said before, we close this switch to apply a 72 watt load at about 10 milliseconds into the simulation. So right about here, we apply the load, and you can see the ripple starts to increase after we got that heavy load. And prior to that, it's pretty flat at about 170 volts. So again, we've got like 160, 170 volts coming into this buck converter. And as we apply a heavy load, we get some more ripple, but basically it's 160 volts. We also measured this output as we apply this load to see what it looks like. So let's take a look at that now. We're going to add the V out to this trace, and we're going to get rid of the V in, and we're going to auto range. And here is what we got in the previous video, the simulation, where we start out and it goes up to 12 volts coming into the load, and it wiggles a little bit and then it flattens out, and suddenly at 10 milliseconds we apply this 72 watt load, and you can see instantly drops down to 10, but then immediately this PWM controller senses that voltage and says, hey, we got to adjust the duty cycle to fire this MOSFET so that we return our voltage. And you can see it recovers immediately, but it's only up to a little over 11 volts. So what we're going to talk about in this video is what we can do to improve this response so we get up to the expected 12 volts. And what we're going to do is we're going to focus on this buck converter. And we're going to see, we use some kind of arbitrary values in this buck converter. So we're going to see, well, what really will affect that and what can we tweak to make our response a little bit better to come back to 12 volts. So as you can look at this buck converter, basically it's being switched using this MOSFET. And we have, first of all, our switching transformer, and we have kind of an arbitrary ratio, which is basically 300 millihenries on the high side winding and 10 millihenries on the low side winding. And that gives us a transformer ratio that in LTSpice is equal to this 300 divided by 10, which is 30. And you take the square root, and that gives you about a ratio of about 5.5, which we have up here. So if we're getting, say, 150 volts on the primary, we would expect 150, you divide that by 5, and you get maybe 30 volts secondary. And if you figure the average, if this is a PWM signal, the average might be 15 volts, something like that. So we know we're kind of in the right ballpark, but maybe we can adjust this transformer ratio to give us more voltage on the secondary or something. So we get, instead of recovering to 11 volts, we recover to 12. Here is another thing that we can look at, which is this inductor, all right? And we saw in the actual power supply, the inductors that are being used are really big inductors. And this is only a 10 microhenry inductor, kind of an arbitrary value. Maybe we can increase that to give us a better response. So we're going to also look at increasing this to be substantially more than it is and see how that affects the output. So we're going to look at this transformer and we're going to look at this inductor. So first let's try changing this ratio and trying to increase the secondary voltage. Maybe that will help us to recover to 12 volts instead of only 11. So what I'm going to do is I'm going to increase this inductance, which lowers the ratio, which should maybe give us a higher voltage on the secondary. So I'm going to right click and let me pick. So instead of 10 millihenries, I'm going to put in 30 millihenries. And then what I'm going to do is I'm going to run this and see what we get for an output. Okay, so I've changed it to 30 millihenries on the secondary to give us a lower ratio and hopefully a higher secondary voltage. And here is our output voltage versus time. And you can see 10 milliseconds, we apply the 72 watt load and it goes from 12 volts down to, yikes, it's down to around 6.5 or 7 volts. And it seems to be flattening out. So yeah, that probably wasn't the best. So maybe adding more inductance in your transformer isn't going to help you. So let's take a look at the other thing that we can do, which is modify this inductor. And again, we said this is 10 microhenries arbitrary value. And in the real world, if you look at an ATX power supply, they've got some big inductors in here. So let's go and put this back to 10 millihenries on the transformer and crank this up to a higher value and see if that helps us. Okay, so I've returned my transformer back to the same ratio of about 5.5. I changed this back to 10 millihenries. And I've increased this output inductance to 50 microhenries, or 5 times. And here's the simulation. You can see immediately when we apply the load, it goes down to 10 volts and immediately goes back to 12. It bounces around, of course, but it looks like it's going to recover to our 12 volts that we wanted. So it looks like we've got a fairly nice working buck converter, and it returns us to 12 volts. Now, of course, the devil's in the details. In a real buck converter, you'd probably use MOSFETs here instead of diodes. and you'd optimize it. You get the general concepts here of how this buck converter works. Now, the next thing we're going to look at is, like we said before, in a real ATX power supply, you have something called a supervisor circuit, which monitors the output current and maybe voltage or power, and senses if it goes outside the acceptable range, it will shut down the power supply. So the way we're going to do that is I am going to add right here a very simple overcurrent sensing resistor, where you basically put in a very low resistance, measure the voltage across that, and use that to sense how much current. So if I have, for example, if I apply 12 volts, I will get 6 amps through this 2 ohm resistor. So this should give me a 6 millivolt voltage drop with that 6 amps current. So I'll take that voltage and I'm going to use it down here in this circuit that's going to control our PWM controller. And as we saw before, there is a run/soft start input. And what we can do is we can basically either allow this to run at the normal 9 volts, in which case this integrated circuit will do its job. We can also short circuit it. We can put it to ground voltage, and that will immediately shut this off. So what we're going to do is we are going to measure the voltage across that resistor using this behavioral voltage source. We talked about that in other videos. Basically, you can assign an equation to define the voltage of that source. And what we're going to do is, if you right click on this, you can see our value. We typed in this equation. If Vout minus Vload is greater than 0.01, so if it's more than 10 millivolts across that resistor, then shut this down. And the way I do that is I have a SR flip-flop spice model. I basically put the reset to ground, and when this goes positive, when this equation is true, it will put a 1 out, otherwise it'll put a 0. So if I put a 1 into this, it will set the output to 1, which closes that switch, which grounds this run SS terminal, all right, which shuts everything down. So really nice and simple way to do it. You just say, hey, if the output minus the load, if that voltage is greater than whatever you want, here I've written 0.01, if we want 10 amps to be detected, if so, close the switch and ground that terminal. So what we're going to do in our case, let's say if we want 6 amps, we can change this to 0.005, since we're going to have, if we apply the load, it will be 6 millivolts. So it's over. If it's greater than 5 millivolts, then shut this down. So now this should, when we run this, it should shut down the power supply as soon as we apply this load. So let's run the simulation and see what we get. Okay, so here's our simulation, and we've set it for 5 millivolts or 5 amps. And when it gets to 10, this should go down to 0. So let's see what happens. So we're 10 milliseconds, and instantly it drops and drops and drops, and here's 0 volts. And you can see it basically shut down the power supply and went to nothing. So that's kind of a good conceptual view of how these supervisor circuits work. It basically measures and then shuts down this PWM controller to shut off the MOSFET so it doesn't have any more output. So now one of the reasons I'm such a big fan of simulator software like LTSpice is what you can do is you can say, hey, wait a minute, we're applying 72 watts load. What if I want 200 watts of load? Or what if I want 400 watts? Is this going to work? And then what you can do is you can try it and say, oh wait, it doesn't recover at all. In fact, it almost crashes with twice as much load. What could be the problem? And then you can start investigating and finding out what's the cause of it not working, what do you need to do, and what do you need to modify to get closer to a real world ATX power supply. So it's a great way to learn. You start thinking about things and you investigate. So I encourage you to look at my videos on LTSpice, learn LTSpice. It's a great way for you to learn electronics and also to verify your circuits. So I think that's it for this one. If you like any of these, hit the like button, subscribe, hit the bell notifications, and most of all, let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.